So welcome everybody. It's also good to hear all the different disciplines that you come from. As we will see, survival analysis applies to a variety of different disciplines. All of them have, in addition to the standard question of time to the occurrence of an event, there's also many other complications that are often unique to your discipline. So for example, the nephrologist will be I'm looking at maybe time to death, but what happens if somebody now is getting dialysis? And they didn't have dialysis at the beginning, and now they're starting to get dialysis. So does that change their risk of death? Well, hopefully it does, right? Or kidney failure or whatever. And so they are intervening events that they have. Those of us that work in cardiology, we are faced with issues that are, what if I'm looking at dying from cardiovascular disease, what if somebody gets a non-fatal MI or gets a non-fatal stroke? Does that change the risk? Maybe they are more frail because they had that, but they get treated and maybe they're better. Or no, they got a cabbage, so now they're doing even much better. So does that change their risk? And what if they die of something else? They die of cancer, not of heart disease, and I'm studying dying from heart disease. So there are little complications that each discipline will be facing. And so those would be nice as we are presenting things that you raise these questions, because you know your clinical discipline better than us. I mean, I'm not a clinician, I'm a statistician. So your input is going to be very helpful. So stay away from that. So I'll stand here. So many of you said that you wanted to understand the basics of survival analysis. So the way the workshop is structured is today, especially in the morning, we're starting with the basics, because we anticipated that a lot of you would require basic understanding. Then we'll progressively get a little bit more complicated, deal with competing risks, deal with recurrent events, dealing with these things that are frailty models and joint models we'll be doing that tomorrow. So today in the morning especially, we'll be talking about survival analysis 1 and 2, sort of the basic things. When you read the literature, what you will see is that many papers, no matter where they're published, whether they are in the New England Journal and the BMJ and Lancet, or in some not so important or fantastic journal, they tend to report analyses in a rather simplistic way. Why? For who knows the reason, but many times it is because it is easier to communicate the results of your study, of your research, when you do simple work. If you do a complex analysis, yes, it may be either more appropriate or it may be one that can tease out certain relationships better than others. But now you have to make sure that that methodology applies, is one. So you have to verify the assumptions are met for it, but you also have to be able to explain it. And explaining this, as many of you say, you've seen this, you've probably read it, you've heard about it, but explaining and understanding is the hardest part, right? So just keep in mind that many papers that are published are simplifications of what one could be doing, right? It's not wrong to do that, but it is what usually happens. Now, one of the things that we tend to do also, or many investigators tend to do, is to assume they understand something because they've seen it so many times, okay? So I'll just ask a simple question, raise your hand. How many of you have heard about the Cox proportional hazards model? Okay. How many of you have heard about a joint model? Okay, only two. Okay, that's good because not many people have heard about joint model. How many of you know what a competing risk is? Very few also. Okay. How many of you know what the Kaplan-Meier curve is? Okay. How many of you know what a hazard is? Is the hazard the same thing as the risk of an event? How many of you say yes? How many of you say no? If you were to explain what risk is to your grandmother and explain what hazard is to your grandmother, can you say different things? Or you would say the same thing? So the technicalities of hazard are very difficult to explain. I think risk, many people say that if you engage in this activity, you will have and one activity could be living, you are at risk of getting something. But what is your hazard? We'll be talking about that because most of what we'll be doing in survival analysis is understanding hazards. And so this is, at least in English, we have two separate words for it. In other languages, we don't. Or I was telling you that I speak Spanish, and in Spanish, risk is riesgo, and hazard is riesgo. Exactly the same word. And so what is the difference? There is an important difference in statistics. So we'll talk about that. So the content of the first lecture is, as I said, an introductory part of what survival analysis is. Why is it so important? Why is it that you find it in every word that you read about it? Then there's some challenges that we have. The issue of censoring and whether it is informative or non-informative is something that is usually not mentioned in any paper that you read. That's a fundamental concept in survival analysis, is this issue of censoring. And we'll talk about it. If you're not interested in it, you can close your eyes when we have the slides on the mathematics of the survival function. But I hope you don't close your eyes so that you understand. And hopefully I can explain it. What is the survival function, the hazard function, and the cumulative hazard function? And then how we go about estimating the survival function. And yes, we will talk about life tables and Kaplan-Meier estimators, but also mention something that we'll be talking more about tomorrow, and that is what happens when we have competing risks and other types of estimators that we have to use instead of a Kaplan-Meier. And many people, even in big journals like BMJ and New England Journal, they do not do it properly. They assume that the Kaplan-Meier is the only way to display a survival function. And when they have competing risks, it is a biased way of displaying it, but they still do it. And so we'll talk about that as well. All right. So where did this all come from? Well, this comes from actually manufacturing in the early part of the 20th century, when the so-called industrial revolution has already taken place. Everybody is manufacturing new things. Electricity comes in, and now they're manufacturing light bulbs. So people were manufacturing cars, they're manufacturing other machines, and machines don't last forever. Machines will fail. And so if you are a manufacturer, you care to sell your product by saying my machine lasts long. The time to when it fails is long. It's not short, okay? So one example of this was light bulbs. Light bulbs are a product. In those days, they were incandescent bulbs with a little filament. And eventually those filaments go. So if I'm Philips, or I am Siemens, or I am General Electric or Sylvania, I want to say my bulb will last longer than the competition's bulb. So I need to know what is the average time my bulbs last. Well, how do I know when the average time my bulbs last is? I would have to take a sample of my production, and test them and see the average time when they die, okay, or when they fail. And what they found is that as time goes by, the proportion that are still functioning starts at the beginning with 1, and eventually, after, I don't know, this is maybe months, 30 months, all of them have failed. So we call this the proportion still function is the survival function. So everybody at the beginning is alive. All the light bulbs are working. At the end of the last bulb dying, we have this. Okay? And so they would plot this. And they had, I don't know, maybe 1,000 light bulbs, and this is what they saw. Okay? And this is what tends to happen, that products, machines, buildings, curtains, clothing, all of these things fail at some point. And you're interested in the failure of it, but you actually will call it survival because you're interested in positive things, not in negative things. So we talk about what is the distribution of the times to failure. So survival is looking at the failure distributions or distributions of time to failure. Now, if you notice this, it is not a normal distribution. It is a skewed distribution. It is going down like that. And if you remember your statistics course, first course in statistics, you studied mean, median, mode, all of these things. And you knew that the mean for a skewed distribution is biased towards the extreme. So it's bigger than the median, which is halfway through. And most people walking the streets and buying light bulbs don't know that feature. The people that make light bulbs know that feature. They never advertise their median failure time. They advertise their mean failure time because it's bigger. And they can say, you know, here it's the life is 1,000 hours. And most people that buy these, they say, oh, I'll buy this one because it's 1,000 hours. And they say, oh, that stupid one, I'll not buy it again. It only lasted 800 or it lasted 700. Why? Because you were looking at the mean, they're likely to fail. A lot of them start failing early. There's some that will last long. Right? And so it's a skewed distribution. And so you're interested in time to failure, but we are in the health field. We're not interested in light bulbs. We're interested, well, here the light bulbs. Let me continue with the light bulbs. We tend to see that that curve, this one here, looks like this one, this first red one that goes this way. Okay, so that's the exponential distribution. And so things that fail tend to follow an exponential distribution, but not really that well. Somebody has looked at it, and there's a better distribution that fits the data of failure better than the exponential distribution. And it's called the Weibull distribution. The Weibull distribution is actually a generalization of the exponential, which means that the exponential is a special case of the Weibull. Say that again. So the Weibull is a generalization, meaning that it covers different types of a family of distributions, and it has what's called a shape parameter. And the shape parameter is called beta. When beta is equal to 1, then the Weibull becomes the exponential. But it can have other values, and it'll has different shapes for that. So the survival will be high here and then coming down if it's exponential. But here you have people that are, or we can start later, you can have people that are going like that and coming this way. You have different shapes for it. Now, why don't we use the Weibull distribution, even though it seems to fit the data better? Because, for example, it can handle increasing, decreasing, constant failure rates. Those of you in pediatrics, it's a good one to use for aging and for infant mortality, for example, or looking at random failures at the same time. So it has a more nuanced application for survival analysis. Why do we use the exponential most of the times? Because it is simple to explain. It is very simple to understand, and it is one that it has some nice properties. It is memoryless. No matter where you start, you always continue with the same. You will see that when we do the fancy models like the Cox model, the exponential distribution comes in. And we will see that Cox proportional hazards model uses the exponential distribution. And you will see that there is other proportional hazards model that use the Weibull distribution. But people don't use those. Why? Again, because it's easier to explain. But there's another reason too, and that is that these methods are what we call robust, meaning that they are generally widely working fine in most situations. Only if you want to be able to fit the data perfectly do you use the more nuanced. So that's why you see less and less of them. But I wanted to mention that there is this. So in general, the exponential distribution is just a special case of the Weibull when beta is equal to 1. So this is for light bulbs. But as I said, we're not necessarily interested in light bulbs in this course. We're interested in humans. And humans, here's plotting the mortality rate, the failure times in India. And there were 3 different surveys that were done. In 1971 is in blue, 91 is in red, and 2013 is in gold color here. Things haven't changed much. They've come down a little bit, right? But it's still, you have this sort of U-shaped relationship. And so how do we model failure times here? Well, failure times, if I'm talking at younger ages, at this point, it tends to be exponential, maybe Weibull. And then here, it's 1 minus the exponential of Weibull. But here it's sort of flat, maybe it's increasing with age a little bit. And then we start using models. We don't model the whole thing, we model parts of it. We look at it. That's why when we select patients for our studies, we take a given age group, etc. Because we don't include children, or we take adults 19 and above. We have it like that, that's more. So the exponential seems to work earlier. Okay? Actually, the Weibull would work better. But we tend to do exponential in general. So we'll be seeing that here. So our question, all of your questions and why you're here is when in whatever discipline you're interested in wanting to know this. The probability of surviving past some time point t. So if the probability of surviving time is capital T, that's the random variable. You want the probability that survival time that you have is greater than some time point t. What is t? 50 years, could be 90 years, could be whatever, or could be any time. We denote this by S of t. But more important than that is not knowing that. We want to know if there are other factors, and we use x in a bold is a vector. Oh, by the way, I think we're going to give them the slides, right? So don't worry about taking pictures of slides. Pay attention. Yeah, they're circulating these. Yeah. So you will get them, so just don't worry about that. So we're not only interested in surviving past some time point t, we're interested in what factors may influence that probability. So is the age, is smoking, is obesity, is fitness, it's having other diseases, it's whatever. There's so many things that can affect your surviving past some time point T. Now, one thing I haven't mentioned that I should mention, and it'll become apparent later, is that at this point, we're talking about surviving, and the term survival comes from either you're alive or dead. The people that came up with this concept of survival were people that were working in life insurance companies. And life insurance companies chose their name, life insurance, when they really are working on death insurance. Nobody insures your life. They insure your death. But it doesn't sound like a good marketing tool to say, we want you want to insure your death, so please give me money. No one would do that. So they do life insurance. They change the wording to life. They construct life tables. They call them life tables. They're death tables. Their death tables are, given that you're this age and this sex, and whether you smoke or drink or this or that, what is the probability that you will die in the next year? And if it's high, it will charge you a lot of premium. If it's low, I'll charge you less. Okay? And so the first people that started dealing with this outside of the life industry people, the clinicians and epidemiologists that started looking at humans failing in disease, were always modeling bad outcomes. And it was time to get in a heart attack, time to get in cancer, time to a relapse, time to get in an infection. But always bad things. But the technology also applies to good things. It's time to discharge from hospital, time to remission, time to get in pregnant if you're unable to get time, whatever. So you can have good things as well. The methodology doesn't distinguish between good and bad things. It's time to an event, a clinical event. We also started calling these failure distributions. And the first textbook on survival analysis came out by Prentice, and he called it failure time distributions. Quickly changed it to survival analysis later, thanks to the life insurance people talking to them. All right, so we're interested in time to surviving some time point event. So it is time to the occurrence of some event. So let's look at an example. I've made up some artificial 5 people in a longitudinal study. So we have people A, B, C, D, E. A, B, C, D, E. And we measure things on them at baseline. So everybody gets measured at baseline. And this person entered here at the same time, this person entered later, and so forth. We measure them 5 months from when they entered, so that's the other measurement. And at 12 months, we intend to measure them again. Now, 2 of these people had the outcome that we're interested in, and that's this one and this one. And maybe this is when we ended recruitment, we got all 5 people, and this is when we're going to analyze it. Now, at the time of analysis, when we're doing this, what happens? We have this person had the event. This person, we followed them for their full 12 months. We stopped following them. They did not have the event. This person, we followed them and did not have the event. This person, we followed them, did not have the event. This one did have the event. So we only have 2 people that had the event occur to them. So do you say, is it 2 out of 5 that had it? Well, that's one way you can think about it. But what if so this person here, at the time of analysis, they could have had the event in this little period here, but I did not observe them because I had stopped observing. If I had done a interim look at the data, and we'll be talking more about interim looks in the second workshop, If I had decided, oh, this is going to be 5 years of observation, not just 2 years, but what if I'm randomizing some people to get an intervention, some people to not? I need to monitor the study as it's going along, and I have to do it halfway here. So this is supposed to be maybe 2 years. At 1 year, I'm going to look at it. So at 1 year, I don't know that these people are going to have the event. What do I do? We'll have 0 events in both of them. Okay? Or if I have one in one. How do I know what we have? So if the outcome is a measurement, we don't have it occurring in these. But if it's an event, what can we do? So we talk about the issue of right censoring. So censoring is not political censoring. It's not censoring of books or whatever. Censoring means here that I just do not get to observe the outcome. And survival analysis has the unique feature, and this is the sort of the most important issue with survival analysis, is that it's censored. It's right censored. So we have to deal with the censoring. We know that they are still at risk for getting it, but it's going to occur sometime later. So the actual time to failure is not observable. Now, one of the other features is that that censoring can be informative or non-informative. And we'll define this in a second, in the next slide, the next 2 seconds. So censoring can be of 3 different types of censoring. Censoring is either right, left, or interval censoring. Left censoring is when you're studying some event, but you've started observing the person now because they entered your study now. And let's say your event, I work in cardiology, so I'll talk about heart attacks. So suppose they had a heart attack before they entered the study. And I'm interested to know when that occurred, the timing of that. But I don't know when it occurred. I know it occurred, and it happened sometime in the past. I can ask them. They may remember, may not remember, correct date. So I know it happened before the observation started. So I only know it occurred, or before a certain time point, but not when it occurred. So I cannot actually use the time of follow-up information properly, the time from that heart attack to the next heart attack. The other one is, I'll talk about the next one is interval one. I'll come back to right censoring. Or no, I'll go in order here. Right censoring is when you don't know the exact event time, only that it occurs after the time point. So I've stopped observing or following this person because my study funding ended, or because this is an interim look and I'm just making a cut point in time, and anything that occurred before that I look at, and anything that occurs afterwards I'm not. So I say it's right censored when you don't know the exact event time, but if it occurs after a certain time. And that's the most common thing that we have. We have right censoring. Interval censoring is because we may know when it occurs, but we're not observing exactly the date when it occurs. So for example, in a study where I'm looking at the outcome of death, we know from death certificates when it occurs, so that doesn't happen. But if I'm looking at an outcome that is having a heart attack that's non-fatal, and the people are coming to visit me in the clinic every 6 months, and if they get a heart attack and they get treated somewhere else or whatever, that's fine. And I may not get access to that hospital record, or nobody can remember. I just know that it was between the previous visit and this visit, sometime in that interval. That's interval censoring. Usually when we're doing studies, we tend to try to avoid this by having an outcome where it's going to be in some hospital record. But if we have, for example, some people have as outcome brain functioning, looking at cognition and looking at how they perform in a particular test of cognition. And if they go below a certain value, then they met the event. or they go above certain value. Well, now we give them a test at one time point, we give them the test at another time point. Ah, but they've crossed it now. Oh, but they crossed it somewhere in between. When did it occur? I don't know. Because we're not testing them every day or every minute. And nobody's registering this when it's happened. So we have done that. But the most common thing is the right censoring, because we stopped following something. Now, when we do the right censoring, the censoring can be what's called informative or non-informative. Informative means that the reason a subject is removed from the study is related to the event being studied. So suppose you're doing a longitudinal study, you're following patients, and they're supposed to be coming in every 2 months or so to have and talk to the physicians and nurses about their situation, participating in the study. And let's say the study is looking at obesity. And so now you have to have them come and weigh themselves. And all of a sudden, somebody doesn't come for their 2-month visit. You call them on the phone, you do this, that person doesn't come. So the last time you observed them was 2 months ago, and now they're lost to follow. So you say, okay, they had not reached the event yet of their BMI coming below a certain threshold, so they have not had the event. Is the event occurred or not? I don't know. I will not know. But do you think that the reason they did not show up is related to their BMI? Most likely, yes. We don't know. We never know. But it could be that they were embarrassed to say that they increased instead of decreasing or whatever, and therefore they just dropped out. So that could be potentially, it's usually informative. Non-informative is what we want it to be, that it was a random reason why this person value or observation of the event is there. So being centered is random, unrelated to the risk of the event. My study ended. I arbitrarily decided I'm going to analyze today. This person lost their job and left the city. Hopefully that they didn't lose their job because they were sick and related to the event, but they just did that, or something happened, right? So usually you want it to be non-informative. When we have informative censoring, we have a complication. We call it a competing risk, and we'll talk more about how to deal with competing risk. But most of you said, you know the Kaplan-Meier. How many of you have known that the Kaplan-Meier requires you to have non-informative censoring? Nobody says that in the paper because they assume that whoever wrote the paper knows that, because that's a key assumption of the Kaplan-Meier, that the censored people are not informative. But so they will not mention it because usually they haven't checked it. They'll just assume so. And they assume that the readers don't know that that's what it should be. So now when you read that or you're reviewing a paper, you'll say, how did you know that your censoring was non-informative? Then you trust them. And depending on what type of censoring, when they censored, was it an administrative censoring? Because my study ended, and so that's people that have not had the event by the end of the study. That usually is an administrative censoring, so that's probably okay. But if it is lost to follow-up, that could be informative. So then they have to justify to you in the paper, why did you assume that the people that dropped off the study were non-informative? Okay. And most people don't. They said, oh yeah, we did time to event analysis. One of the reasons you see that most papers on clinical research of longitudinal data, and especially randomized controlled trials, their primary outcome of the study is time to some event. Why do they choose time to some event? Of course, I'm assuming that it is because that's the clinically important question. But if they say, oh, I'm interested in preventing heart attacks, it's very different from I'm interested in delaying heart attacks. Or I'm interested in preventing death is very different from I'm interested in delaying death. When HIVs first came out in 1980, 81, everybody that got HIV progressed to AIDS and died. So the first studies were saying, oh, if we studied this medication versus placebo, and my outcome is dead or alive in 2 years, I have 100% died here and 100% died here. Useless outcome. But oh, can we delay time to death? So now the outcome is not, or the endpoint is still death, but the outcome is not a binary yes or no in a given time period. It's time to an event. That's when they started using more and more this. So that's one reason that it's important, because time to the event is the research question of interest. But the other, it has a nice little other subtle result. If I'm studying death in 2 years and somebody is lost to follow-up, ooh, after a year, I don't know if they died or not. So I have missing data, missing outcome data. What do I do? Then I have to do imputation, or then I have to do worst case scenario, all these problems. But if I'm doing time to event, I never have missing data. Because when they're lost, it's censored at the time they were lost. So everybody has the outcome of time to follow. So that's a nice little trick that some people figured out. And now everybody uses, that's why all those papers do time to event, because never have missing outcome data. But the question is, the reason you lost them, did they die of an opportunistic infection and you did not know about? You didn't have whatever you were studying. Let's say you're looking at time to get in, time to get in AIDS from HIV, and they died of something else. So then it's an informative censoring or not becomes the issue. And they don't mention this whatsoever. So be careful when you're reading things, that one of the key assumptions of this Kaplan-Meier estimate is that it is not informative censoring. All right, so let's look at how does one go about calculating this, right? There's a visual that I borrowed from Professor George Howard, because I like the way he explained this. And so it's the following. Suppose you have these people enter a study. It's a longitudinal study. At the beginning of the study starts here. This is the end of the study, administrative end of the study. And what happens? Well, people enter at different time points. No study has everybody entering at the same time. This is just a fact of life, right? So people come at different events. Some people get the event. Some people drop out of the study early for some reason. We will assume it's not informative. Okay? These people get to the end and they're censored because they got to the end, and then there's what, 1, 2, 3, 4, 5 that got to the end. So we have the event occurs, we have premature censoring, or we have end of study censoring. Now, how do we analyze it? The first thing we do is we don't use calendar time. We use follow-up time. So we move everybody to the left artificially for the analysis. So everybody starts at time 0, and their follow-up time now is whatever it is. So now some people have, if we assume that this early censoring person was uninformative, it's just like any other censor. So we assume this person is censored. That's one key assumption. Then we have those 5 events that we have. We pull everybody there. Next is we want to calculate the survival function. How do we go about doing it? Well, if all of these were events, then I could get when do people die? And I can just say, oh, this person was alive here. The proportion that were still alive was this. The proportion still alive was this, as we go along in time. Very easy. But how do I deal with the censor? That's the tough part. So how did we do it? Well, so we take that same one. Now we make this look a little complicated. We have 10 people here. So we have 10 time points at which their follow-up time ends. And some follow-up time ends when they have the event, and some follow-up times ends when they're censored. Okay? So we have 10 different follow-up times. And now what we want to do is to say, what is the probability of survival? So these define intervals of time. The probabilities of surviving different time intervals. So what's the probability of surviving from 0 to T1? Well, they have 10 people, and everybody survives. So that's probability is 1. Now I come to probability, the second interval, T1 to T2. And this person, there's no events that occur. There's 9 people that come in here, right? Because this one was censored. That's gone. We have 9 people that enter, and 9 people survive. So everybody survives that, also 1. What's the probability of surviving the next interval, T2 to T3? Well, 8 people enter, but 1 dies. So 7 out of 8 survive. So I can do it for each interval by saying how many people entered and how many people survived that interval. So I can calculate probability of surviving each particular interval. But here comes the crucial thing. I cannot survive an interval until we get to it. I have to get to it. So to survive this interval, I have to have survived these other intervals. To survive this interval, I have to survive these other intervals. And so the probabilities are multiplied to do that. Okay? And how are they multiplied? Like this. So I have the intervals, I have those 10 intervals. The probability of surviving that interval is calculated here. Those are those numbers that were up there, 1, 8, 6, 8, 3, 6, 7, etc. Those are these. The probability of surviving through the interval is that. And until people surviving that interval and through the interval comes from what? Comes from having survived the previous ones of that. So that equals the probability of the first one. And now I'm taking probability of surviving the next one, still 1. Here, it's still that 0.88 and survived the previous one. Now it's 0.786 and 88. So I have to have this times this will give me this. And this times this will give me this. And this times this will give me this. This times this will give me this, etc. And you have to have survived that interval and surviving through that, having survived the previous one. And so that's how it's done. Nobody does it by hand. I just wanted to show you this so you realize where these things are coming from. And this is then what you're interested in is the probability of surviving through that time point. And when we do that, we get that function like that. So I'm just plotting those there. This is what Kaplan and Meier suggested in 1958. Both of these were actuaries, and one of them was a statistician and an actuary, working for life insurance companies. Because this is what they did. They said, how much conditional on the fact that you reach the age of 42, so you survived up to 42, what's your probability of surviving the interval between 42 and 43? If it's large, then I'll charge you less. If it's small, I'll charge you more. And then they realized that that's the product of those previous surviving intervals. So they call it the product limit estimate. So their name for it was product limit estimate. And an interesting trivia fact is that the most cited statistical paper, but also the most cited medical paper in the world is this paper. Imagine that. This one paper published in the Journal of the American Statistical Association in 1958 is the most cited paper in the world in the medical field, by far. We'll tell you what the second one is. All right, so they came up with this, and well, as it turns out, the estimation without censored observations is just simple proportion. How many people were in total included in the study, and how many were still surviving past time t. But it's just a simple proportion. And this is what we call the 1 minus the empirical cumulative distribution function in statistics. But their trick, not trick, but their insight was how to deal with the censoring. And with censoring, what you're doing is you're taking the people that are at risk in the ith interval and how many survive the ith interval, but having survived the previous ones and multiplying the probabilities before. And this is it. This is what gave them this most cited paper ever. Well, the other reason it's most cited, you know why? I said it already. But most studies of RCTs and randomized controlled trials that are published in the New England Journal are doing time to event. So you always descriptively do a Kaplan-Meier. So Kaplan-Meier is cited in almost every clinical paper. That's why they're good. A little trivia. Okay. Everybody okay now with the Kaplan-Meier? Questions? Would you be able to explain this to your grandma? What is, yeah. Well, you mean the time in the interval? No. It's a non-parametric method here, right? We're just saying whatever interval you survive with. Now, if it's a wide interval, then chances are that people will fail in that. So then your interval becomes smaller. But no, it doesn't. The time there is not. That's why you have the steps here. The steps here are based on those time intervals. Now you will notice also that the curve at T1 there was a censored person, and the curve did not change. At T6 and at T7 there were no failures, so the curve did not change. So when people are censored, they go out of the risk set, but the actual survival probability doesn't change. So they would call it a step function. If you have many people and yet steps are closer, it looks a little more smooth, but in general, it is always a step function on that. And the steps occur depending on where the timing is of this thing. But the calculation of the probabilities does not. Yeah, so the steps are, remember we had 5 events? We had 1, 2, 3, 4, 5. When you see this in papers, sometimes you will see at the end, they have a flat one. And they usually will keep it until the last person followed. But you know that no events are happening, that's why it's flat. So it only comes down whenever there is an event occurring. It stays flat or comes down. It stays flat, comes down. The poor patient fixed it when they die. So the time intervals you don't fix. See, the time intervals where when this person was censored, when this person had the event, when this person was censored, those are the time intervals. Right? The time intervals are, this is the same plot, I guess, when this person was censored and then. So it's determined by the data.
By the event.
an event. So, no, it determined, those time intervals are determined by either a censoring or an event. But when you do the calculation, you will see that the probability of surviving through the interval doesn't change unless there is an event. Came down here when there was an event, but now there was no events here, so this did not change. Or no event here, but this did not change. So it only changes when there is an event. So that's when it goes down. That clear? So the time intervals are what you've observed. They're not what you determine. Now, once you construct the table, the plot, now I can look at this at any time interval I want to. Or I can look at it two different ways. I can say, at what time point 50% of the people are still surviving. So then I go to, this is 50%, and I go to, I come down here. This time is when 50% are still, whatever this is, I can say this is 17 months or so. Or I can say, let's say this is month 12 at 1 year. How many people are still surviving? Now I go this one, go up, and I say, 63% are still surviving. So the construction is based on what is observed. Interpretation is based on whatever I want to do. Do I want to interpret looking at a specific time point, how many are still surviving? Or do I want to know at what time point do I have 20% failures? Or what time point do I have 40% still surviving? Then you can go that way.
I had another question. So, if your endpoint is dying, it's very easy because you only die once. But if your endpoint is something that is dynamic, so if you have an MI and that is one endpoint, but then within another 3 months, you have another MI. So you are looking at this MI as the endpoint, but that same person goes on to have a second MI. So where do they fit in this curve? Or you can't look at it like that?
Right. So that's tomorrow.
Okay.
That's a complication. It's a real life complication.
Okay.
So this was designed for a
Definite
unique
endpoint.
occurring event that we call a terminal event. That light bulb fails. The car broke down. The human died. That's it. Or the person, sometimes you have it in cancer, you will have time to relapse. But once they relapse, and that's bad. So yes, so it is a unique occurring terminal event. But once you relapse, you cannot not relapse. Or time to pregnancy. Once you're pregnant, right? Now, if you're looking at multiple pregnancies and you're looking at multiple heart attacks, and you're looking at those are multiple recurrent time to events. That's the complication that we face, and that's tomorrow. You have to go slowly at that, right? This is the easy part. Time. So when you have some things like that, multiple MIs, the standard easy way to do it is time to the first MI. Then this handles it. Now what did I do? They had a second one. What do I do with that one? The standard way would be to ignore it. And people don't want to ignore it because that's information. How do I recuperate that information properly is tomorrow. All right. So the Kaplan-Meier curves, if we have several groups, now we get a Kaplan-Meier curve for one group. And, oh, yeah.
The probability of them dying based on the events. How does it get affected by, say, the first event happening? Is it affected by how frequently the events are happening, or is it mathematically it doesn't matter?
So each person can have the event only once.
Yes.
So yes, it is. Once you die, you die, and you cannot die again. And everybody has their own time to death. And so there isn't a recurrent event. In her example, you can get multiple MIs. That's a different situation, right? It's a more complex thing. But here it's time to a uniquely occurring event. And my time to event is not affected by your time to event. They're all independent observations. You'll always assume that the individual patients are independent of each other. Now, there may be other factors that lead to somebody having a different probability and having the event. That's when we're going to do modeling and take into account their sex, and if they smoke or they do alcohol. This is a crude analysis that just is showing us, describing the mortality rate, or the survival distribution, unadjusted for anything. We'll talk about how do you adjust it for other.
My other question was regarding the initial graph you showed, where you said that the patient enters time, and then there's this fixed time after which an event or censoring occurred, and then we move the whole thing to the left.
Yeah.
So these people who came in later in, I think it's the previous.
Yeah.
So the people who came in later into the study,
yeah.
say for example, the second person, yeah, he had to be alive for that X amount of period before he was actually recruited into the study.
Right.
But when we shift the whole thing to the left, does that make a difference? Like, we know that because this is the event is death. So this patient actually was alive before that,
yeah.
But we are presuming, what are we presuming? I mean,
yeah,
I just couldn't.
Good question, because what we're assuming is that this person at baseline meets whatever criteria I had to be included in the study. And just like this one did, this one did, this one did, but they may have prior history, right? They have a lot of prior history. Everybody has lots of prior history, yes. But we are ignoring that prior history. Or if we measure it, we will know, like if I'm looking at time to death, oh, have you smoked for how many years? Have you had previous heart attacks? Have you had this? Have you had that? Did you do this? Did you do that? Etc. So we have a bunch of other things, and we say, somewhat artificially, these are baseline characteristics. And I will now see, when I do the modeling, I will take into account those baseline characteristics and see how they affected the probability of survival or not of that person and collectively of the group. But yes, we are ignoring the previous one. So let's say this is not death, but this is a heart attack. What if they had a heart attack previously here, right? I'm not using that information. In fact, it's left censored because I don't maybe know exactly the date of the heart attack. But at here, I can say, I can ask them a question. Have you previously had a heart attack? Yes or no? And now I have yes for this person, and I can try to model that. So everything that occurs before the person is recruited becomes what we call baseline. It's baseline. If I want to know the time of that previous one, if I want to include that in the model, the time, that would be less sensitive. Yeah, because we don't have that information. Don't have it. For that person, their follow-up starts from the day they're recruited, which is very artificial. I mean, I could take them from birth. Now people actually are not doing only from birth. They're taking it from pregnancy. And they're taking mother's exposures to pollutants and whatever environment. So they call it primordial prevention of things. That's a whole different thing. But now for simplicity, we say, once I've included this person in the study because they met my eligibility criteria, now we start at time zero. Information. Yeah.
What happens to the Kaplan-Meier curve if more of your participants come towards the early part of recruitment,
yeah,
as opposed to almost 80% joining just before the study time, because most of them would get administrative censoring?
Right. So if everybody comes at the beginning, you have longer follow-up times. You may have a better picture. If you have people, because you don't do your study well in recruiting, and you get 2 years funding, and you only are able to recruit in the last 6 months, you're going to get, as you say, exactly a lot of administrative censoring. You will get almost no information. Your
So how do we
curve,
figure that out when we look at a paper? Like, how do we know if it was early censored or actually how do we figure that out when we look at the KM curve?
it's hard to tell, especially in large studies that were long duration, right? These are details that they don't publish, but you could, if, for example, the Kaplan-Meier curve, let's say everybody came in late, so even those people came in late, you may not have this event would not have been there, right? This event may not have been there. This event will not have been there. You will have fewer events.
Fewer steps.
So your Kaplan-Meier curve may be like that. So if you see a long horizontal bar, it means that, and they put it all the way up to here, then you know that there is, but see what they will do is they will not do that because they know that people will see it. So they will just do this, and then stop there. Say our follow-up time was, our study was truncated early, this and that. Blah, blah, blah.
So if you see more steps towards the end, that means it's a red mark for the study, as opposed to more steps towards the early part.
No. So
More steps.
less events is what is the issue.
In the sense, more events towards the end.
It's not.
If you don't have enough steps, that means it's a problem.
You can't really guess that easy.
Okay.
It depends on so many things, right? How the event rate is. If the event rate for chronic diseases is long, it's small, right? But if it's a infectious diseases or the outcome is a flu or diarrhea or things like this, you'll have lots of events that occur quickly. So you don't, even if they recruited towards the end, you'll still get it. So they need to tell you things like our original recruitment period was such and such. This is our recruitment rate. You'll see, then all of a sudden that. Those things, that's dirty laundry that they will not show you. If you now request it from the study team, can you tell us how your recruitment, they may or may not send it. So it's very hard to tell what's going on.
So ideally, papers should also publish their this thing.
What they should do and what they do, who knows, right? Full disclosure and transparency is nice, but most people don't do this. It used to be that people would argue, the journals would argue there's no space, or the authors will say the journal says there's no space for this, but now you can put it on online supplementary. So ideally, it would be nice if they publish these sources. So you just have to read between the lines almost to figure out. They said, our recruitment rate was this, or we aim to get so many people. And if they say so, it's difficult to get people. Now you know, okay, so they had took a long time to get people, but they won't tell you this.
Yeah, this is.
Say that again? With censoring or without censoring? Oh, how do you construct it? So if there was no censoring, what happens is you have, in our example, you have all 10 would have been events, right? So we know exactly every time point when somebody died. I can now plot the time when everybody died, and I know at this time point somebody died, and so the proportion surviving is 1 minus over the denominator. So at the beginning, all right, let's see, this example. So suppose all of these were X's and died, right? So this person died here. So now I'll have the probability of surviving this is 9/10. Then I come here and another person dies. There were 9 that entered and 8 survived because 1 died. So then it would become 9 entered, and 1 died for 8 nines. And this becomes 9, 10, 8, 9, 7, 8, 6, 7, 7, 5, 6, 4, 5, 3, 4, 3, 3, 2, 3, etc. So it keeps going down because the numerator goes down as well as the denominator goes down. Because always somebody dies. And so that's why the calculation becomes a very simple, how many have died so far versus, or how many have survived so far divided by the number still alive. It's just a simplification. Maybe this way, it will turn out that if the number at risk, this is always one person dies there, then this, if you, oh yeah, that's right. If you take one person dying here all the time, it becomes, things cancel out. So you'd have one person dies, you have, let's say you have 10, and this is 10 minus 1 is that first interval. And now you have 9 and 9 minus 1, and then you have 8 and 8 minus 1, and you keep going. And so what happens is that this cancels, etc. And so you will get down to 0 out of 1, so 0. But at any time point, you could say out of the proportion out of 10, how many have survived it? So just mathematics, things canceling out. Yes.
I don't know. Your question is about the number, total number who came at the early part of the study or later part of the study. That you cannot figure it out from the Kaplan-Meier. Only what you can figure it out, that whether the events are happening at the early phase of the study or later phase of the study. Then if the curve is dropping very fast, that means that people are dying or leaving the study. Censoring happening. There are two things. That is what you can look at it. If you wanted to see that, one of the reason why, yeah, that is, you cannot figure it out whether the people came early or later and so on. Even if you put your numbers at each time point, how many are available, that doesn't tell you that information, I came early or not. It deals with the total, that is a denominator.
The only way that you would find out would be if they gave you this information. And nobody gives you this. Okay, so we know now how to get the Kaplan-Meier curve for a single group. But in our research, we never just look at one group. Yes, maybe we're doing a cohort study and we're looking at that. But now we're interested, oh, in my cohort, do males do differently than females? Or in my cohort, those that had this severity of condition versus that severity of condition, do they do different? So now what we want to do is compare curves and get separate curves. So we can get separate Kaplan-Meier curves for each group, and then we can compare them. We can compare them visually, and then we'll be talking after the break on using standard tests like the log rank test. And then we talk about testing those differences in survival functions. Why? Because people are not just happy with seeing things, they love p-values. And so we have to do p-values because they like it. So now we have to test the differences in survival distributions with censored data. And we can do it crudely with the log rank test, not adjusted for covariates, or we will do then, we'll talk about how we do it adjusting for covariates. But that's comparing survival curves. Now, mathematically, instead of considering differences in survival, we consider differences in the hazard for two reasons. Mainly, well, maybe, I think it's actually really for one reason. One reason it is mathematically easier to do. Now we've convinced people that the hazard is an important thing to look at because it's easy to model the hazard instead of the survival. And what is the hazard? The hazard is We call it the immediate chance of death, conditional on being alive. That means given that you've arrived at this time point, what are your chances of dying in the next short increment of time? This is what the life table people do. Given that you reach the age of 48, what is your probability on the next interval? For them is the next year. That short interval of what is the probability that you will die between 48 and 49? So that's the hazard, the conditional risk of dying, different from unconditional risk, which is, doesn't matter. What is the risk of dying between 48 and 49? Whether you were that is surviving that interval. You have to survive the previous ones too. That's where the hazard comes. And so mathematically, it's easier to do calculations working on the hazard. But what is the hazard? It is the chance of dying in the next short period, conditional on still being alive, which means not having had the event. And nicely, the life table people have a fantastic word for it. They never called it the hazard because these life table people or life insurance people were working with death tables, right? So if you're dying at a higher rate, it means the force of mortality is heavy on you. It's a strong force pushing you down to die. So they called it the force of mortality. And it's like, I love that term. If the hazard is high, the survival curve is falling fast. If the survival curve is not falling fast, then the hazard is small. You think about it as the force of mortality on people. So for every hazard curve, there is one and only one survival curve. So this makes it, I want to compare survival curves. So I can compare hazards, and if the hazards are similar, then their survival curves will be similar. If the hazards are different, then the survival will be different. There are two different functions. They're different functions, but they go hand in hand, one on one. They only one survival curve for every hazard curve, and vice versa. So if we understand the hazard curve, then we understand the survival. And since it's mathematically easier to work with the hazard, that's why we work with the hazard. So what is the hazard? Well, first of all, let's look at the survival curve and the hazard curve. So remember they had the exponential distribution is one that looks like this, the survival. So it's a skewed distribution that's going down, and the rate of going down depends on the hazard function. This one is higher hazard, and this is a 1/2, this is 1. And so it's coming down steeper here. Okay? And the hazard then is a horizontal line, either at 1/2 or at 1. And we can have different, and you can't read this, we'll get a better example later, but we have different survival functions, we'll have different hazard functions. And they go hand in hand, like the yellow one goes with the yellow, etc. And we'll give it a better example later. And people have looked at different types of survivals and hazards and how to interpret them. There's all sorts of different ways of looking at it. But let's look at a simple example. This is old data, 1963. Probably is a study that would have been unethical to do today. It was people that had leukemia, and they were in remission, and they had been given some sort of intervention, like maybe, I don't know if it was some chemotherapy or not, and in remission. And now they're studying times to relapse. Relapse is a bad thing. And there were 42 participants, and they were doing a randomized controlled trial against placebo. So it says, okay, they are now in remission. Should we continue to give them whatever chemotherapy or not give them anything? Which you would probably say, we can't do that. Anyway, this is what they did back then. And the question is, do the remission times differ between the groups? This is how they asked the question back then. Because survival was not a big issue. People were not analyzing survival. In the papers from the 1960s, you don't see much of that. Why? Kaplan-Meier came out in 1958 in a statistics journal. By the time that makes its way to biostatisticians and makes its way to clinical researchers, it's in the late 60s. Okay, so that's why you don't see it. Right, but in those days, they published their paper data for small studies, so I got it from the paper. And what do we have? Well, in the standard, which was placebo, this is the months you're in remission until they relapse. So 2 people relapse after 1 month. 2 people relapse after 2 months. 1 after 3, 2 out of 4, etc. And by the time 23 months had gone by, everybody that got placebo had relapsed. Horrible. In the intervention arms where they get in the chemotherapy, relapses don't occur early. First of all, there's not a single relapse for 6 months. So they're lasting longer without relapsing. And this one must have come in late because the pluses here are people that are censored. So here I observed all the time points. But here there are many people that came either late or dropped out or something because I don't have they didn't relapse. So this person after 6 months of follow-up was censored. But I had 3 that relapsed at 6, 1 at 7. These are censored, this relapse here. And so we see that the last relapse was at 23 months. And these people came in early and lasted a long time because it was a 3-year study. And by 36 months, we didn't have it. So when I did the Kaplan-Meier, this is what it turns out to be. So this is the people in the intervention. This is the people in the placebo. What do we notice? The hazard is strong. Here people are dying or relapsing at a quicker rate. Here they don't start relapsing until 6 and they start coming down. And then nobody after 23 months, here everybody has already relapsed, but here nobody more relapses, so it's flat. And I can analyze it either way that I want it. Now, if I want to compare the curves, what do I do? How do I compare the curves? I just did. If my grandmother had leukemia and was in remission, I would say, you better tell your doctor to keep you on that chemotherapy because I want you to be in the blue, not in the red. There's an incredible separation. It is just so much better to be in that one than the other one. I don't need any statistics to give me a p-value. It is so obvious. However, journal editors love p-values. People think that p-values are the only thing that matter. And so they want to do a p-value. So how do I compare them? Well, I can compare them at a specific time point. At 12 months or a year, how are they doing? And I can do a test. How many people were still at risk in this group and how many had survived and how many people, how many had died and how many had relapsed and how many of people are at risk, how many had relapsed, how many people are at risk. And I can do a 2-by-2 table and just calculate, well, Fisher's exact test or a chi-squared test if you like chi-squared test. I would prefer Fisher's exact test. Yes. 21 and 21. So having the same number of participants per arm is not necessary. No, the survival curve is constructed within a group. So let's say the placebo group had fewer people and the intervention group had, so one of them had 15 and the other one had 30. Okay. Whatever their experience is, the one with the fewer people will have fewer steps. The other one will have more steps. The confidence interval and uncertainty around the estimate of the survival curve will be wider for the one with fewer, and will be more precise or more tight for the ones with more.
More large number of
Yeah, but it doesn't affect anything else.
Okay, so if in chemotherapy patients, if we any given any so more leukocytes is common in chemotherapy patients who are undergoing chemotherapy. So if I give any toothpaste to them, so that for chemotherapy patients toothpaste, so in that the gum health is reducing.
Okay.
So good for the gum health in that. So oral leukocyte is also reduced by removing some ingredients in the toothpaste. So we can do this study in that.
So what is your outcome? Is it tooth health, gum health?
It's not knowing the outcome. It is my hypothesis is by giving the toothpaste, the gum health and then more leukocytes becomes something reducing compared to that.
All right. So okay. So if your outcome is the measurement of the leukocytes, then it's not a time to event. It's a measurement of some continuous variable. So none of this applies. Then you would have to say, at what point are you measuring your continuous outcome? So it's after 2 months of treatment with the toothpaste, or the other alternative toothpaste, or not. What is the mean leukocytes or log mean leukocytes here and log mean leukocytes there, and do a t-test or something like that, but not survival analysis. Survival analysis is time to some event occurring. So if you say that it's time.
But that if we randomized control type, we can use this.
Yeah, you can use any other outcome. What I'm saying is that, yes, for randomized controlled trials, your outcome can be continuous, can be binary, can be categorical, can be, we'll talk about types of outcomes that one can have. They vary, and depending on the type of outcome is the type of analysis. But what I said earlier is that most people will choose a time, an outcome that is a time to an event for the reason, one reason, or two reasons. One should be because it's the most clinically meaningful thing to do. For you, the meaningfulness is leukocytes. But for them, it may be heart attack. That's an event. And they can say, oh, I don't care whether it's an event occurs or not. I want to know the time to it. But when they say time to an event, it has the other benefit is that it's never missing. Because when they're censored, you still have some time.
Another example, if you're taking the COVID-19. So the COVID-19, after that symptoms occurs, only they are seeing the diagnosis at the time only using that. So in the COVID-19 patients, there are also death occurs. So mostly there is a death sensor data. Sometimes we can see in the COVID-19 patients. So
what is that word? Left censoring of what?
Left censoring is we can't diagnose before that the patients may occur. After that only the screening procedure they will come and see.
So what is your outcome? COVID?
Outcome is a death occurs
Death.
or not?
Well, there's never left censored because if they're dead, they're dead. They're not in your study. So your outcome is the one that is left censored or right censored. Death is your outcome. It's not left censored.
Okay, during diagnosis, we can see the diagnosis time if COVID-19 occurs or not.
We'll have to talk later because I'm not understanding which is your outcome. Is your outcome time to an event? What is that event? Is it COVID or is it death?
It's COVID. Okay.
Getting COVID, time to getting COVID.
Time to getting COVID. So we can't know the biological concepts of disease. Natural history of disease, biological concept we don't know. If it is
Right, so it is left censored.
mostly
The
left censored.
date of onset is not known.
Yes.
But usually what people do then is they start their study on people that don't have the event. So if somebody already has COVID, they're not eligible to get COVID, right? So then they're not included in this. So that's the typical way that people do it.
So in this curve is the more sensor data means we can differentiate that between these two curves by
So-
marking the sensor data and that survival curve.
Yeah.
So with that we can able to differentiate everything. If it is scale,
No, censoring is not what you're interested in differentiating. You're interested in differentiating the survival, or how many people, what proportion of people are still not having the event. That's what you're interested in. You don't care about the censoring. Censoring is a nuisance. It's a problem that we have to deal with in this kind of data. It's not what you're interested in.
because some survival curves the sensor data marking is there.
Yeah, you can mark it, but it doesn't do anything.
Do anything. So we can't be able to justify that. Here there's more sensor data that in that curve itself.
But if there's more censored data than not censored data, who cares? I mean, people will mark it because the software can mark it for you, makes it pretty or makes it ugly.
That's I don't doubt in more survey curve some
Yeah.
more sensor data and some less sensor data.
Now you would see it and notice it that, I mean, here, if you know that the number of people are the same, you can see the steps here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here there's 1, 2, 3, 4, 5, 6, 7. So there's more censoring in the top. But when the censoring occurs, do you care? And if the number of people is 8,000 people, there's so many steps you would have. And yes, if you see a flat thing, you know that likely we're censoring, but I don't know anybody that's really caring about when censoring occurs, because censoring.
That's only we are seeing.
Yeah, but censoring can be because people came in late or people came in early and dropped off. So because this is already on follow-up time, not on actual real time, you don't know. I don't know anybody that has ever been interested in actually when the censoring is.
I have a question related to the reporting of KM curve.
Reporting up?
KM curve, this KM plot.
Oh,
So
okay.
let's consider I have a trial. The primary outcome is time to first of heart failure or all-cause mortality. It's an individually patient randomized trial. I have to randomize let's say 2,000 patients. After randomization, my protocol says that the patient will be followed for 36 months. The total recruitment time is for 18 months. Now I have to make a KM curve. When I plot a KM curve with all the participants till the last time, I see something like this. And I see that there are, let's say, 10 participants towards the end of follow-up who are at risk. When I plot it with the confidence interval, I see very huge confidence interval out there. Now there's a paper by Peter Austin where he talks about the reporting of KM curve. And he says that if you have very less participants, though you will be analyzing all of them with your CPH, but you will be showing, it's better to show till you have your tight confidence intervals and you cut it short. Let's say if you have 3 years of follow-up and you have very less number of participants at risk after 2 years, you cut it at 2 years. So what are your thoughts on that?
Oh, I agree with that. I think it's, one thing is, this is the estimate of the survival curve. We haven't talked about any estimate has confidence intervals you can do for it. So I can do a confidence interval for this one and a confidence interval for this one. And the confidence interval is constructed always looking at how many people are at risk at that point. And so the more people are at risk, the more precise the confidence is going to be. And so it's going to be, if I drew it here, it would be, like that, and it starts widening as I have fewer people here at risk, it gets wider. And here, also the same thing, it gets wider. And so the software will do it with whatever, but the question is, how confident are you in reporting things? So what, yeah, Austin says, I agree. You can choose an arbitrary point, it's arbitrary also, at which you feel personally that you have sufficient number of people that my confidence interval, I will trust my confidence interval in being less imprecise. And that's a personal judgment. You can decide when you want to do it. But anytime you do something like that, you need to be transparent and say, we arbitrarily chose this because the number of people at risk after 2 years was less than 100 or less than 50, whatever.
Should not be doing by any chance because I'm showing in Kaplan-Meier is descriptive.
Yeah.
I'm giving descriptive, I'm only describing how it went on in the trial.
Yeah, I mean, so this is different points of view, right? So some people say, I just wanted to give the curve. Other people say, why aren't you giving me some confidence intervals? So now you put confidence in. Then they're so messy because you have so few, and then and sometimes you will have, it looks like it's going up there when it's actually not going up. But it's the uncertainty is going up, so it makes that broader. And it leads to improper interpretations in the tail end. What do you have to do then? If you want to be totally transparent, you present that, you present the confidence then for the whole thing, and now you have to waste a paragraph in your paper explaining why you don't believe it. That's why people do this kind of stuff. They truncate it because they don't want to spend that extra paragraph explaining that that is meaningless because of this, this, and this, and that. And so that's all there is. So it's, if you want to do it, you do it. If the Food and Drug Administration asks you to do it, you do it. If they ask you to truncate it, you truncate it. You do whatever the Food and Drug Administration asks you to do. But in general, it's you as the investigator deciding how to present and wanting people to interpret that. You interpret it for them. You say, if I want to present it, I'll present the uncertainty, but I will explain it in that extra paragraph saying, you know, we have very few people here, don't make a big deal about it. You say it, not let it to the reader to make up the hypothesis.
The concept of hazard has been very clearly explained. The chance of having an event in the next period conditional on still being airline. Censoring sounds musical, but could you repeat what that exactly translates to? Sorry, it's a very fundamental question.
No, very good. So censoring is a way, I mean, the best way to explain it may be that, let's say you are a patient in a study and I'm following you. Okay. If you have the heart attack, I am following you, so I know you had the heart attack. But at some point in time, I stop following you. You are still at risk of getting the heart attack. I just don't know about it. So you may have a heart attack. I finish my study November 30th of this year, and tomorrow you have the heart attack. You were still at risk for that. Your risk never changed as a person. But I don't have the opportunity to observe. Now, let's say you are a very important professor, right? So that if you have the heart attack, you are in the newspaper. And I will find out about it. And oh, Professor Mohan had the heart attack. Could I use that information in my study? No. Why not? Because I did not give everybody else in the same chance of being observed. Just because you're famous, you were in the newspaper, but not everybody else. So I have to censor your information at the time at which so it's inability to observe the outcome after a certain time. Now, if you had been in my study and not had a heart attack, and on August of this year, you left the study. You moved out of India, you went to Singapore or whatever, you escaped, and I don't know what happened to you. You may have had the heart attack in August. You may have had it in October. I don't know. So I'm censoring you at that time. Now, if the reason you moved to Singapore was because you were going to get treatment there for your condition, now that is potentially an informative censoring. The reason you left was related to your condition and your risk amount. That's informative censoring as opposed to uninformative censoring. But if I have informative censoring, I have a problem. I have a bias now. Because the people that left are the ones that have higher risk. And so I'm going to have an artificially inflated lower risk when it shouldn't be. So how do I deal with it? That's when we have competing risk and competing events, which is negative. That makes sense? Thank you, sir. All right. So survival analysis, we tend to talk only about clinical trials, but it's for any longitudinal study. It applies in cohort studies as well as in clinical trials. You study the time to the occurrence of some clinical event, which I like to call endpoint. And the outcome variable is not the clinical event. The outcome is time, there's a random variable, time to the occurrence of that event. And so what we observe is the minimum of 2 time points. Either you get the event, and it's the time that you got the event, or the time to when you were censored. We observe only one of those 2. We get the event, we observe this. If we don't observe the event and we stopped it administratively or you dropped out, that's the time to censor. That's the censoring part. And this is the theoretical survival curve. Remember, the first slide I had was, this is what we're interested in. The probability that you survive past some time point t. That's what we're interested in. It sort of looks like this. It looks very exponential. That's why we use the exponential. But as I already argued, Weibull will probably fit it better. But assuming that it looks like this is just a diagram. The hazard rate, those of you that remember your calculus, it is just related to the first derivative or the tangent of that. That's what it is. So geometry, calculus, is this the tangent. So it's just taking the first derivative of the survival curve adjusted by the survival. Because conditional on surviving up to that time point, it's the first derivative. And there's a great paper, you can't see it here, but it's in the notes. It talks about the geometry of this. And so you see here, this hazard here is very different from this hazard here. The force of mortality is bigger here than it is here. You're failing at a higher rate than you're failing here. So that's what we're interested in. Can we modify your hazard? What explains your hazard? Can we model your hazard? That's what we tend to do in survival analysis because of this relationship. So the hazard rate function, if you want to close your eyes, you can close your eyes and don't care about calculus, is that, as I said, the first derivative or the limit of in that next little instant of time that you failed in there. And we can integrate that and get what's called the cumulative hazard function. And the survival curve then is basically the exponential function of the cumulative survival function minus the sum. Or just minus that. So you see that these are all related. If you tell me the hazard, I can get you the survival. You tell me the survival, I can take the derivative and get the hazard. That's a one-to-one relationship. And we study the hazard because it's mathematically easier to work with that function than looks like. I'll have it this that is then an integral over. Okay, so again, people sort of conceptually understand survival. Not many people conceptualize hazard. So, for example, if I have a survival function that looks like this, suppose that's exponential, or it looks sort of exponential, what would be the hazard for that? It should be a sort of flat, should look like that. And it's relatively small because you are not dying at a hazard rate. So it's pretty much the hazard is, now you're thinking about this. It's like this. So see, these are not changing much. There it changed a little bit, so it changed a little bit there, but it then stayed flat. The hazard is staying flat. If it's coming, the survival is coming like that. What if I have this survival function? What is the hazard function for that? Is it going to be another horizontal line? Most likely, yes. Is it going to be higher or above or lower than this one? Higher, because people are failing at a higher rate. It's going to be there. So it's the opposite. When you're failing, survival is that, the hazard is higher. What about this one? We find this that in some studies where it's chronic disease, people that are healthy are not dying, they're surviving early time points, and then they start, as they get older, they're gone. So what is that hazard? What does that hazard look like? It should be small at the beginning and going up. It should go like that. And in some studies where you have this one, what would you have? So here you have, in surgery studies, post-surgery, you have huge hazards of dying. And then as you stabilize and you get better, your hazard, you survive. And then as you get older, maybe it goes up. So what is that hazard? It's very steep, very high start, and then it comes down, and it's almost nothing there. Maybe there's a little tip going up at the end. So it's hard to visualize hazards. We always tend to think about this, and we feel we understand this, but there is a one-to-one relationship, one to the other. Yeah. Well, everybody starts on the same point.
But over here, they start at different points of hazard function.
Yeah, because here my hazard is this, even at this point it's that, and the other one is that. So this is less than this. The slope. The hazard is the slope, right? Which is the tangent, the first derivative. So if you think about it, you can go like this and see, okay, it's very high here, and it's very almost nothing, almost zero here. Here it is not zero, but it is more than this one. This is a little bit steeper than this one. So that's what I argue. It's very hard to understand hazard, but that's what we model in the Cox model. We model hazards. That's why I want to try to visualize what a hazard means. A high hazard, if it's constant, like this one, or more or less constant, it's easier to interpret. That's why we have exponential distributions, because the exponential distribution is a constant hazard. Real life is not a constant hazard. So therefore, all of our models are approximations to real life. Most of them are pretty good approximations, but they're not perfect. Because it's hard for us to visualize or understand a hazard that is this. But I explained, this is, for example, if I have doing a surgical study, post-operative hazards are high, and then they go down. Or I may have people that are healthy people, and I'm looking at people that are healthy, but then they start deteriorating. This is what happens in some cases. So whatever clinical discipline you're in, you know the hazards that you have, or you can figure out your survival, you estimate the survival curve from patients that you have that are similar. Now you can then get the hazard from that once you have the survival. We'll have other examples of survival and hazard. So for our leukemia plot, that was our survival by group. So I just had it in a different software now, different colors. And this is what their failure by group is. This one minus the survival. I'm assuming there was no competing risk. We'll see how that differs with competing risk. But sometimes you plot survival or you plot one minus survival if you are pessimistic and want to talk about deaths or failures or bad things. You go that way. What would the hazards be there? It's kind of funky because they have few observations, not just few. So the hazards clearly are higher for the placebo group than for the other one, which is pretty flat most of the time. It's not coming down. The other one is, it comes down, but because at some point here, it wasn't so drastic, you have this crazy dip, basically pretty high hazard there. And if I do the cumulative hazard, it looks sort of like this one. They look about the same there. The different hazard, different values. It looks similar. We'll talk about cumulative hazard estimates later on. So how to present results of an RCT? Most people do not present survival curves in chronic diseases because survival curves means you have to start at 1 and come down. And when people don't die or don't get the event, like this one is looking at the outcome of major vascular complication in patients with an MI after a non-cardiac surgery. And they would have had to start at 1 and come down, but look, they come down only up to about 16 or so. So this would be 0 to 100, and survival would be just like this here, and they would look very close to each other. To show the separation, people show it and do 1 minus the survival. And they'll present the incidence in this case. And this cumulative risk of major vascular complications. So now comes the complication, and I'll stop here for the break. Yes. Yeah.
In the curve that you showed with the hazard versus the original one, this one. So my question is, the hazard, when you're saying one, the brown line and the green line, they start at different levels. So is the baseline the T1 when you had originally shown us that timeline? Is it a T1 or is this 0? I mean, I know it says 0 here.
It's at 0. Time is at 0, but
how can you say that at 0 there were that many people who died? That's
nobody had
or the
died.
chance of dying was
The
that
chance
much
of dying
higher.
in the next instant, right immediately after 0, like in the next, so you are recruited in my study, your chance of dying in the next microsecond is that high.
High. Okay. So if your T1 is high, that point, that first frame, if that is higher, you will start at a higher value on the hazard function.
If
Is that
it's
it?
steepest, if it's
Yeah,
coming
the
down,
steepest
yeah.
one.
So
Okay.
that's why we had here, everybody starts at 1 here, right? Everybody is alive, but here it immediately comes down after that little time point, I guess 1. And here it doesn't start coming down to here. So it's pretty flat here, and then it stays sort of like this. But here it's like that. And so then that's why here this stays pretty flat. This one starts higher and goes even higher.